In this lecture, we're going to continue working through Chapter 9. We've already covered Section 9.1 with Section 8.5. These are the remaining Chapter 9 topics. In Section 9.2, we're going to find out why the elements show periodic trends in their atomic and ionic sizes. There are three main themes to this section, with several details listed under each theme. Note that we'll borrow the idea of Coulombic attractions from Section 9.5 to explain effective nuclear charge. Once we understand effective nuclear charge, the periodic trends for atomic and ionic radii are easier to rationalize. Let's begin. The sizes of atoms and ions are determined by the interactions between their positively charged nuclei and their negatively charged electrons outside the nucleus. We can describe the electrostatic principles in a very generic fashion by recalling that opposite charges attract, like charges repel. As the size of the charges increase, so too does the size of the attraction or repulsion, and shorter distances will also increase the size of the attraction or repulsion. There's a better way to quantify this information, though. If we peek at Section 9.5, we see there's a formal definition for quantifying the relationship between two charges, Q1 and Q2, the distance between them, and the resulting Coulombic attraction or repulsion. We see that increasing the magnitude of the charges or decreasing the distance between the charges both have the effect of increasing the magnitude of the attraction or repulsion between the charges. If we apply this idea of Coulombic potential energy to the atom, we see that we must consider the attraction each electron will have to the positively charged nucleus, as well as the repulsions between the electrons. Since the electrons are at varying distances from the nucleus, they will experience different degrees of the positive charge from the nucleus due to core electrons shielding the nuclear charge. We call the charge experienced by an electron the effective nuclear charge, Z sub F. The effective nuclear charge will be less than the actual nuclear charge, Z, due to the amount of shielding, S. For example, if we look at the electron configurations of sodium and magnesium, we see they both have 10 core electrons. Sodium has a plus 11 nuclear charge, while magnesium has a plus 12 nuclear charge. The 1 valence electron in sodium and 2 valence electrons in magnesium are both going to be shielded by their 10 core electrons. However, since magnesium has a larger positive charge in the nucleus, the electrons of magnesium will experience a larger effective nuclear charge than the lone valence electron in sodium. If it helps, I've included Slater's rules for calculating shielding here for the current example with the numerical results. Don't feel obligated to memorize these quantities. The take-home message here is to understand that core electrons will contribute more to the shielding of valence electrons than the other valence electrons. The exact calculations are included on these notes pages for reference. If we shift back to a more qualitative view, we see that effective nuclear charge increases from left to right across a period and increases going down a group as the positive charge of the nucleus increases. This has direct consequences on the size of atomic radii, since some electrons will be experiencing a greater effective nuclear charge than others. As the effective nuclear charge increases from left to right, we see that the atomic radii decrease in size. Even though the effective nuclear charge is also increasing down a group, the effect of adding another principal energy level that is farther from the nucleus necessarily causes the atomic radius to increase. What if we compare the relative sizes of oxygen and sulfur? Both elements are in group 16, but oxygen is in the second period while sulfur is in the third. Since sulfur has valence electrons in the n equal 3 principal energy level, it will have a larger atomic radius than oxygen. If we compare oxygen and fluorine, we see that the higher effective nuclear charge experienced by fluorine will cause its atomic radius to be smaller than that for oxygen. We can also compare the radii of ions to their neutral counterparts. If we remove an electron to form a cation, we wind up with a smaller radius because the remaining electrons are pulled in tighter to the nucleus. If we add an electron to form an anion, the repulsions between the valence electrons will increase, leading to an increase in the radius. We see these trends very clearly demonstrated in this figure where all of the cations have a smaller radius, shown in green, compared to the neutral atoms, shown in yellow, and all of the anions, shown in purple, have a larger radius than their neutral atoms, shown in pink. Let's take a closer look at chlorine and chloride. A neutral chlorine atom has 17 protons and 17 electrons. A chloride anion has the same number of protons, but 18 electrons. We predict that the additional electron in the chloride anion will increase the electronic repulsions, increasing the radius of the anion respective to its neutral atomic counterpart. In fact, we observe that the anion will have almost twice the radius of the neutral atom due to that additional electron. We see this trend in increasing positive charge, decreasing the radius quite dramatically for cations formed from the main group elements. The effect is more subtle, but definitely present for anions of the main group elements, where an increased negative charge results in a larger radius. Let's bring everything we've discussed together with a final example. We're going to rank chloride, potassium, and calcium ions in order by size using only the periodic table. To do this, we need to count the number of electrons, the number of protons, then make a prediction given what we've learned about effective nuclear charges. We see that each of these ions has 18 electrons, making them isoelectronic. Chlorine has the fewest number of protons and calcium the highest. When we compare nuclear charges, the number of protons, to determine the strongest attraction between the nucleus and the valence electrons, we see calcium with a +2 charge will have the strongest attraction, resulting in the smallest radius, while chloride will have the weakest, resulting in the largest radius. We can write them in order of increasing size from calcium to chloride for a final answer. As always, I'll leave you with the parting thoughts of the authors.